Hey guys, welcome to Let's Talk Algorithms. My name is Venkatesh, and today we'll be solving the problem evaluate division. So this is a medium level difficulty problem. Let's look at the problem statement first. Equations are given in the format a by b is equal to k, where a and b are variables represented as strings, and k is a real number, as in floating point number. So let's look at an example. So given a by b is equal to 2, b by c equal to 3. So we will be given queries like a by c, b by a. Using the given formulas, we have to evaluate the queries basically. So if you see a by b is 2.0, b by c is 3.0. So if we need a by c, which is basically if you do a by b into b by c, b cancel each other, and you have a by c, which is like 2 into 3, 6. So and we need b by a. So if you know a by b, the reverse is b by a, so it's 1 by 2, 0.5. And we need a by e. We don't have a by e, so if you don't have, if you can't evaluate certain expression, you return -1. And a by a, basically same values, you return 1. X by x, basically some basically variable which doesn't exist in the given formula. So you return -1 again. Uh, yeah, I mean, let's start a workbook, try to solve the question. So given a by b is equal to 2, b by c is equal to 3, a by c, see a by a, things like a by a is like very straightforward, you can easily do it. And b by a is also fine, you just have to reverse the given query and given variable or formula and to see if you have b by a, which is basically 1 by 2. Things get tricky when you have transitive relations like a by b, basically a by c, right? This is fine. I mean, even this is like just one level of transitive relation, which is basically goes from a by b, a to b to c. But imagine if you have like c to d, d to e, f, and the formula, one of the query was like a by f. So when you're looking at this level of transitive relationships, then it gets trickier. So one way to, when you lay out the problem like this, you can already see, you can consider these each of the variable as a node in a graph, and the edges has the weight of whatever the formula is. Like example, a by b is 2, so this weight carries 2. Um, so you could have all the given variables and their relationships represented in terms of a graph, and do a depth first search. Depth first search because you're looking for the shortest route to the destination, and the first DFS helps better than BFS in that kind of scenarios. So, but what happens, like DFS and given like storing all these things as notes and doing a DFS actually helps to get to a solution. But imagine if your one of your query was f by a. So this is a reverse relationship. You don't have a reverse relationship given. So you have to prepare your data structure in a way that it can handle relationships in both ways. As in, so when you have a to b, so what we'll end up doing is basically in the program, if you have a to b, when you store that in the data structure, you store both a to b and b to a. B to a would be the value whatever 1 by v, where v is the value. So when we are preparing the data structure, we have to take into consideration all these things, make sure the inverse transitive relationship also is supported from the data structure. And when you do a DFS and if your data structure already supports these kind of values, then your DFS is like fine. So let's start coding basically nodes and DFS. So the result is a floating point array. So let's make an array. Excuse me. Load 64. The length would be length of queries, right? So how do you want to represent the data structure, right? Like given A and B come like this as a array of or a list of strings. So like if you're looking at a key value data structure, apparently hash map, right? But how would you want to store relationships? So let's say you basically have to represent a node structure, right? Like your node should contain what does your node usually contain, right? Like example, you have a node A. Your node should contain all the edges, basically where the edges point to and the destination of the edges, right? And then at value at all these edges. So you can either make a custom type, custom struct type, which represents all this stuff, or you can actually simply have a map of type string to map actually. And this map would be string to float. So why is this? Because let's say you have A by B. So we want A. For A, we would store something like A points to B. So you have B to whatever value is like 2. C 3. So you see you have the source node, you have all the edges basically to each of these destination nodes, and you have the values. So yeah, this kind of data structure works. Let's create a map. Let's call it M. Go language likes minimalistic variable names, so let's keep the variable names very minimal. So we have string and value is a map of string type float 64. All right, so you have a result, you have a map. Just before the map initialization, you can just check for corner cases. If length of equations is equal to 0, you don't need all the processing, right? So you just return the empty result. All right, let's start with the calculating gathering the data structure, like gathering all the values into the data structure. For I is equal to 0, I less than length of values, I plus plus. If you check first, basically, if equations of I and 0 exist in a map. If it doesn't exist, basically that key doesn't have a map. So you just create one. Map string float 64 0. So what you're doing is basically, let's say you're starting with A by B. So now your equation is basically, like this. Where is the input? Yeah, your equation is like this, A, B, and you're looking at basically equations of 0, which is A. So does A has a value yet. I mean, does a key A exist? If it doesn't exist, then you create it. If it already exists, then what you do is basically you assign the value. So map of, get the map of, get the value for the key, A. This gets the value for the key A, and then this is basically destination. Then you put values of I. You can do something similar for the reverse. So let's say now you have A by B. So let's also store the transitive relation B by A. Here in this case, B by A. That is it. So now we have our data structure ready. So as I said, the data structure represents something like this. Now A will have B2, C3. Now, when you do A by B, we also store B to A relationships here. All right, let's prepare a DFS method. Let's prepare the initial signature first. Man, right, func, let's call it DFS. So what would this DFS expect, right? You expect a source string, destination string, and let's have a result which we pass to the DFS, and you get the map basically which has all the values, right? String map string float 64. It's a big declaration. Also, when you're doing DFS, right, like you need some way to make sure that you visited certain node. Otherwise, if you have a circular like relationship between two nodes, you'll end up like traversing them forever. So let's have a scene. Go doesn't have set, unfortunately. They want to keep the language very minimal, so they have basically you could use a map as a set. And this DFS returns a float 64 result value. Let's fix the indentation. Right. So you have the data structure, you have a DFS method. Let's call the DFS method. For I is equal to 0, I less than length of queries, I plus plus. So you call the DFS of queries of I 0, queries of I 1, source and destination, and then you can pass the 1 as the result, default value, and you pass the map M, and you need a hash map, which can be used as a set, scene. Let's initialize scene here. It's a map of string to bool to remember you visited certain node. All right. You have for this thing, and your DFS returns a value. Let's call it result of I. Remember, we made a result array in the start. All right, finally, you return the result. All right, let's finish our DFS array. Let's start with directly the exit conditions. When do we exit DFS, right? If you get a key, basically a start value, which doesn't exist in the given map, like our whole data structure, then like Basically, the OK gives you whether a certain key S exists in the map or not. If it's not OK, it's a Boolean flag. So you're checking the negative condition. And if it's already seen of S is true, then you return -1 because you either already seen it or the key doesn't exist in the data structure. Now that we know that the key exists and we mark seen as true, S as true, and if source is equal to destination, remember we have A by A, B by B. In that cases, you have to just return 1. So if S is equal to D, source is destination, then you return 1. If not, then you take the map for a certain start. So this gives us the start. Like example, if S is A here, if S is A here, then you will get this map in the next. Next contains B and C. So we have to visit B and C, range of next. What you'll do is basically you will call DFS again internally here. Except the new start would be C. C is basically example here. If you go, this is B. B is the new start now, but your destination still remains the same because you are looking for actually the destination value, C to D. And then you multiply the previous result with current value. Why? Because A to B is 2. When you are doing DFS, which eventually leads you to C, you need the cost between A to 2 before you calculate B to C. So you do R into next of C, and then you pass the data structure M map scene. If R is basically not equal to -1 here, then bingo, we got the value. We return R. At the end, for whatever reason, nothing worked, then basically you just return -1. So that is it. We have a data structure which parses the input formula, given input, and then creates a data structure in a way that we can handle transitive relations and also inverse transitive relations. And you have a DFS which basically takes care of traversing through the given node structure and find out the associated costs in moving from one node to the destination, like start node to destination node. Let's run, see if it works. Right. So what's wrong here? Equations of I1. You know what? There is a closing thing here. Memory limit exceeded. I'm pretty sure we're not exiting certain loop properly. So you end up I is equal to length of queries. Let's check the DFS. I'm pretty sure we must not be exiting DFS properly. If MF is not okay and seen of is, you know what? Here it should be R. You either see there is a no start node in the given data structure or it's already seen. Either of the cases you return. So let's try. Let's cross check other conditions. Alright, it's finished. Output is 1010, but actually the expected values are 6 and 3. Alright. the output and expected are not the same. Let's try to debug. So make sure our data structure values are properly put in. If you have equations IO not available, you create map for IO. If you have IO already available, then you create a value. You know what? This is 1 by values of I. Still doesn't match. Okay, let's fix other stuff. As long as our data structure is good, we should be fine. I of 1, I of 0, 1 by values of I of 1, I of 1, right? And we start from 0 to length of values, which is good. For I is equal to 0, length of queries, I plus plus. You initialize the scenery. Result of I is equal to DFS of queries of IO, queries of I1, and you pass 1 scene. Alright, the DFS call looks fine. You have start and destination strings, you have result R, you have map. Alright. If you check if M of S is available, if it's not, or if it's seen already, you return -1. You mark seen as true. If S is equal to D, you return. You know what? If start is equal to destination, that's basically our one of the exit condition where we return the result. If you see 6, 3, -1, 1, -1. All right, looks good. Let's submit. It's accepted. 0 seconds runtime. Beats 100% of the Go solutions. Man, it's a new question relatively, I think. But still, it's 0 milliseconds, so not bad. All right, let's go back. So if you're looking at the time complexity, let's look at the time complexity. You're basically processing the input queries linearly here, often for that. And your processing of k is the number of queries. And for each queries, let's say for every query you have to look up, you have to do DFS of node depth. Like let's calculate. Initially you do time complexity. What all operations do we do here? We process the given values and the examples, equations linearly of n, plus we process of k queries, and for each query, worst case, we do, like let's say you have n nodes, you traverse through n nodes for in the DFS, all n nodes, like let's say this is a worst case scenario. And space complexity is big of, what do you have here? You have a big map, which basically stores 2 into the number of length of equations. So if the length of equations is n, you have 2n for map and some n of K for scene array, right? And of you need some recursion stack, assuming log. All right, this is the time complexity and space complexity. I still think there are a few things I'm missing, but overall, you get the idea. If you have any questions, please feel free to post a comment. And if you like the videos, please subscribe and like the video. Thank you so much.